Basic Food Chemistry. Here we are, Chapter 9, Part 3. We're going to talk about analytical methods to measure the constants of fats and oils. So, what do we do to actually get fats and oils out of a feed or food sample? So, here's some methods that are out there. You can do some acid value, some quantification value, some iodine value, some gas chromatographic analysis of the fatty acids. You can do liquid chromatography and also cholesterol determination. So you can see the actual kind of acid value, how you're going to do it. So basically, you've got your weight of your sample, so many millimeters, and then divided by the weight of the sample, and then you're basically looking at the number of milligrams of KOH that's required to neutralize the fatty acids in 1 gram of fat. So saponification, basically, you're just using hydrolysis of an ester under an alkaline condition to actually separate it out. So here's some saponification values you can get for like milk fats between 210 and 233, coconut oil 250 to 264. Cottonseed, soybean oil are pretty similar, and you can see Lauren. So with saponification number, again, that's the milligrams of KOH required to saponify 1 gram of fat. So this just shows you kind of the methodology behind saponification. So 5 grams of your sample in a 250 milliliter Erlenmeyer type of flask. You add your KOH to it, and then you start to boil it out, and then you titrate with hydrochloric acid using phenolphthalein. I never can say that. And then you conduct what they call blank determination. So again, there's a formula that goes with it, where basically the amount of hydrochloric acid required by the blank, and that's B, and then the S is the milliliters of hydrochloric acid required by the sample. So the iodine number is just the number of iodine in terms of grams absorbed by 100 grams of oil. So the molecular weight and iodine number can also calculate the number of double bonds that are there. So 1 gram of fat absorbed by 1.5 grams of iodine basically has a value basically like 150. And this just shows you how it's all determined, how you get the iodine value. You can see all the formulas there. So the blanks minus the sample and divided by the weight of the sample, and then you have iodine chloride to that, and then any excesses that's unreacted, then it's going to go back into and kind of figure out a number. It's kind of a really long chemical equation to do all this, but just wanted to show you how it's actually done. And with that iodine number, you can get iodine number basically of the triglycerides that are there. So basically, how many double bonds is probably the most important thing. So you can see, for the most part, as we go up, even though I'm showing down, if we go up in double bonds, the iodine number definitely is going up, or vice versa. So the less double bonds, the iodine number is much less. And that's the reason you want to know that. Again, double bonds is going to indicate saturation versus, the more double bonds, the more unsaturated it is. So again, that's a good way to look at those triglycerides and see if they're saturated or unsaturated. And you can also look at compositions by percentage of fatty acids of fat itself. So we got the fat, and of course the fatty acid part of it is just part of it with the glycerol. So you can kind of see what's the composition of actual fatty acids themselves. So you look at, for example, C16 here with 50. So it's fat number 3 that we're talking about here. C16, 50% of that is actually the fatty acid. Whereas you have something like a C10, it's only 10%. So again, you can see the numbers. Look at this one, that's a 20 to 4 carbon, and it's 100% fatty acid. So you also have gas chromatography for fatty acids. So you would extract the fat first, then you go through the saponification process, which is again hydrolysis under basic conditions, or alkaline. And then you prepare methyl ester to go with it, and then you actually do chromatography on methyl ester itself. You determine those peak areas of the fatty acids, and so they can be identified by the retention time, and you compare with the response curve of the standard curve. So this will be, again, looking at the analysis that you're doing with the chromatography. So you can kind of see where their peaks are when, again, looking at the standard curve, you know where all these are going to hit. So 14, 16, then we have the different 18 20, etc. So that just kind of shows you on the column at a temperature of 200 degrees Celsius what the output's going to be for determining fatty acids using chromatography. And that can be also done with triglyceride analysis with liquid chromatography. So this would be an example of what it looks like with soybean oil using a specific solvent and what the column actually is in terms of its number. So you can also look at OE8 containing triglycerides, for example, in like olive oil. And so you can look at the different fatty acid compositions that are there, total acyl carbons and unsaturation that's there. So the 54, 52, 1, 2, 3, 4, 5 number, and the equivalent carbon number that we're looking at. You can also determine cholesterol, so it's an enzymatic determination using cholesterol oxidase. So we take our molecule, we expose it to cholesterol oxidase, and it's going to go through some enzymatic type of breakdown. You're going to get the H2O2 that comes off of it, and then we're going to flush it with peroxidase, and that's going to give you a brown color, which we can then determine our cholesterol content. So again, they're going to use and plot those numbers they're going to get, what absorption rate they got, and then again over time you can actually plot what is the micrograms per milliliter of cholesterol that is in a product. You can also use a gas liquid chromatography as well. So you prepare cholesterol in a butyrate solution, you analyze in the actual gas liquid chromatography system. It takes about 15 minutes, and it's pretty sensitive that it can go to 10 to the minus 7 grams. So it'll give you a good, basically, output of how much cholesterol is in a sample. If you're just going to do your lipid content analysis, you can do a gravimetric method, which can either be done wet or dry extraction, and those are the different models that are used. The Soxhlet method is the one that I'm most familiar with personally that I've done before. The volumetric method is also some by the Babcock and Gerber methods that can be utilized. And most of these are AOAC approved, so they can be utilized, for chemical analysis, but also for any type of research and that kind of stuff. So first on the gravimetric method would be, again, wet extraction. So if you have a wet sample, you want to determine the amount of fat that's in for milk, for example. You take your sample, put NH4OH, mix with it. It's going to solubilize the protein and start to neutralize the actual solvent you have. Then you add about 10 mL of ETOH and make sure it's shaken up pretty good. That actually begins the extraction and prevents gelatination of the proteins. And then you add ETSO, or excuse me, 2O, shake and mix, and then you add, the biggest thing is that petroleum ether. So that'll mix with the fat, you mix and shake it. The Soxhlet method for dry extraction is you have a sample in a thimble, and it's continuously extracted with ether using a Soxhlet condenser. After extraction, the direct measurement of fat by evaporation of ether, and then basically it's weighed. So an indirect method was where basically you would weigh the dry thimble and then weigh it, and then weigh, of course, the sample afterwards. So the method of seed, which is very similar to this, is actually it's boiled in ether. So you would have a sample in a little pack, and then it's boiled in ether, and you'd weigh it before, weigh it afterward, and the ether would extract the fat out of it. So very similar to this, even though it's a dry. So the theory behind it is you treat the sample with H2SO4 or some type of detergent. You centrifuge it out to separate basically the fat layer out, and then you measure the actual fat content using specially calibrated bottles. So again, you got to have a known sample weight. Then you digest the protein and liquefy the fat. You add water so that the fat will be in basically the graduated part of a bottle, and then you centrifuge to separate that fat from anything else completely. So like I said, this is the one I'm most familiar with using. So again, going back to the wet and dry sampling, is if the sample is dry or not. So for example, when you're doing the dry sample, if you're doing like meat or a feed sample or something like that, you actually go through and remove all the moisture out first, so you have a dry sample, and then you would put that in these little. Uh, Typically, it's kind of like it looks like a tinfoil little capsule thing, and basically fold it all out so that nothing escapes. You can see the distillation to some extent call under the sulfite method. You're going to boil this as ether down here in the bottom, and it gets boiling, and of course it is going to trap any of the fat and basically remove it out and vaporize it out. And so you would weigh this sample. These are samples in here. You weigh it before, weigh it after. What extraction weight that's removed is your fat that's removed. All right, so that's the end of chapter 9, part 3. Just gave you some basics, not a real big thing that you know everything in terms of how all the chemical measures and the chemical equations, but just want to know there's various type of methods that can be utilized to determine fat content.